Alright, this is the second video on trigonometric substitution. So here we're going to be looking at integrals involving the square root of a squared plus x squared. In the previous video we looked at integrals involving the square root of a squared minus x squared. So if you're looking for those integrals, check the part 1 video. Okay, so we're going to look at something fairly generic. We're going to look at the square root of, we're going to look at the integral of the square root of a squared plus x squared dx. And for this type of integral, the type of substitution we want to do is we want to let x equal a tangent of theta. Then your differential dx is going to be a secant squared theta d theta. So we'll make those substitutions. Square root of a squared plus a tangent of theta quantity squared. And then the dx is a secant squared theta d theta. We can slide out the a from the a secant squared theta d theta, and then also factor out an a squared inside the radical, and so we have a integral of the square root of a squared times the quantity 1 plus tangent squared, and then times secant squared theta d theta. Alright, we have the identity 1 plus tangent squared of theta is equal to the secant squared of theta. So this is going to be a integral of the square root of a squared times secant squared, and then secant squared theta d theta. All right. We are going to be potentially using the inverse tangent function, which means we need to restrict our domain of tangent. And the generally agreed upon restricted domain for tangent is negative pi over 2 to pi over 2, not including the endpoints, and that's going to be in quadrants 1 and 4. Okay, and so the secant is going to be positive. It's actually going to be greater than 1 in those two quadrants. So the square root of secant squared theta is going to be equal to the absolute value of secant of theta, and that's just going to be dependent on where the theta is. So if theta is in quadrants 2 or 3, then the square root of secant squared would be negative. So that would be negative secant of theta, and that would be if the theta was in quadrants 3 or 4, or it's going to be the secant of theta if theta is in quadrant 1 or quadrant. Oh, hold on a second. I've made a mistake here. The mistake is here. It should be quadrant 2 or quadrant 3. All right, so secant is negative in quadrants 2 and 3, and it is positive in quadrant 1 and quadrant 4. So our secant is, in this case, between negative pi over 2 and pi over 2, so that's going to be in quadrant 1 or 4. So the square root of the secant squared is going to be just secant. Okay, so let us continue. So that is going to be a integral of a secant theta times the secant squared theta d theta. Slide out the a, and we got a squared secant cubed theta d theta. And in a previous video, it would have been in the integration by parts video, I believe, possibly in the trig substitution. I don't remember exactly, but I think it's like the second part of, I think it's in the trigonometric integrals. I think it might be in the second video where we do the integral of secant cubed. And that requires integration by parts, and it's a little bit of an involved integral. So we're going to go ahead and refer you to that video. I think it's part 2 of trigonometric integrals, and let me double check here. Okay, I double checked in my YouTube channel. So yes, the 3.2 part 2 video, that's going to have the integral of secant cubed. So you can go through the details. All right, so you're going to have a squared, and then over 2 is part of the integral of the secant cubed. Okay, and it is going to be secant theta, tangent theta, plus the natural log of the absolute value of the secant of theta, plus the tangent of theta, and then plus c. We'll go ahead and draw in our reference triangle. So this is going to be in either quadrant 1 or 4. We're going to go ahead and just use quadrant 1. So here's our theta, our right angle. Okay, and so we have x equals a tangent of theta, so tangent of theta would be equal to x over a, so it gives us the opposite over the adjacent. Using the Pythagorean theorem, the hypotenuse would be a squared plus x squared under the square root. So the secant of theta is going to be the hypotenuse, the square root of a squared plus x squared all over the adjacent side of a. All right, so we have a squared over 2, secant of theta, and tangent of theta. So we're going to do x times the square root of a squared plus x squared in the numerator, a times a in the denominator, plus natural log, absolute value, secant theta plus tangent of theta. So we're going to add their numerators, x plus the square root of a squared plus x squared all over a, and then plus c. And there is something else you can probably do. You can split this natural log up using properties of exponents, and the minus ln of a might be gobbled up by the constant of integration. But I'm going to leave it at this, and we're going to go ahead and look at the next example here. And this will be an integral, a little bit more concrete integral using the x equals a tangent of theta. So we're going to look at the integral of negative 16 over x squared plus 25. So again, what determines what type of substitution is what do we have under the square root? So the square root of x squared plus a squared. So we're going to let x equal a tangent of theta, and our a in this case is going to be 5. So 5 tangents of theta. Differential dx is going to be 5 secant squared theta d theta. Slide out the negative 16, and then we have the integral of dx, which is 5 secant squared theta d theta, over x squared, which would be the 5 tangents of theta squared. And then to get the radical there, we could go ahead and draw a reference triangle here. So again, we'll put it in quadrant 1. So there's your theta and right angle. Okay. And tangent of theta is going to be equal to x over 5, so that's the opposite over the adjacent. Using the Pythagorean theorem, the hypotenuse is going to be the square root of x squared plus 25. So we're interested in getting that radical there, so we want to use probably the secant, which is the hypotenuse over the adjacent. So the secant is the hypotenuse over the adjacent of 5, so then we have 5 secant of theta is equal to the square root of x squared plus 25, and so we can make that substitution there. Alright, so we have negative 16, let's see, we got 5 on top, and then we have 5 squared times 5 in the denominator, so we got a 5 absorbing, and so we still have 5 times 5 or 25 in the denominator. And we have secant to the first power, I believe, because we have a factor of secant in the numerator and denominator, and then d theta all over the tangent squared of theta. It's going to be negative 16 over 25. Integral of secant is 1 over cosine theta. Tangent is sine squared of theta over the cosine squared of theta, d theta, which is negative 16 over 25. Integral of 1 over cosine times the cosine squared theta over the sine of squared theta, d theta. So negative 16 over 25. Okay. We have cosine over sine times 1 over sine. Okay, so I absorbed one of the cosines. Now I'm writing it this way so that I have 16 over 25 integral of negative cotangent theta cosecant theta. And if you recall, that antiderivative is going to be the cosecant of theta. Okay. Cosecant of theta is going to be the hypotenuse over the opposite side, so that's going to be the square root of x squared plus 25 all over x. So we have 16 over 25. Cosecant is x squared plus 25 under the radical divided by x, and then plus your constant of integration. Okay. All right, well, that's it for this video. So we've in the first one we looked at integrals where we want to use x equals a sine theta. Here this video we did x equals a tangent of theta, and in the last video we'll do an example or two when we want to do a substitution of x is equal to a secant of theta. Okay, so stay tuned for the last part here, and we'll see you next time.